pH is a way to measure the strengths of acids and bases. In the lab, you might use pH paper to quickly tell whether a solution is acidic or basic, based on a color change. But what does that mean to be an acid or a base? Here are two of the most useful definitions. An Arrhenius acid, named after a Swedish scientist, Svante August Arrhenius, is a substance that generates H plus ions when dissolved in water. Bases, when dissolved in water, generate OH minus ions. We use the Arrhenius definition when dealing with aqueous solutions of substances. A more general definition was proposed simultaneously and independently by a Danish chemist named Johannes Nicholas Brønsted and an English chemist named Thomas Martin Lowry. The Brønsted-Lowry concept is based on the transfer of a proton, an H plus ion, from one substance to another. A Brønsted-Lowry acid releases a proton. A Brønsted-Lowry base accepts a proton. The Brønsted-Lowry definition does not depend on the substances being dissolved in water. We'll discuss the chemical behavior of acids and bases more in another video, but for now, let's focus on how we measure the relative strengths of acids and bases using the pH scale. A strong acid more readily donates a proton than a weak acid. A strong base more readily accepts a proton than a weak base. But the amounts of protons we're talking about here is very, very small. The pH scale was suggested by Søren Sørensen, another Danish scientist. It is a logarithmic scale that makes it easier to write the very small amounts of H plus ions that are produced by acids and bases. The equation is pH equals negative log of the concentration of H plus ions. The concentration of H plus is in terms of moles per liter. Is water an acid or a base? A pure sample of water only slightly donates and accepts protons. We say there is a very slight autoionization, or self-ionization, of water. This means that there is enough energy for a small proportion of the water molecules moving around to bump into each other and transfer a hydrogen ion from one molecule to another. That is to say, a small proportion of water molecules break up into H plus and OH minus ions. The rest of the water stays as intact water molecules. The tiny bit of H plus and OH minus generated is so small, we write the concentration of H plus in terms of pH, which uses a base 10 logarithmic scale. The autoionization of water is so minimal that water is considered neutral, neither acidic nor basic, and it has a concentration of H plus ions of 1.0 times 10 to the negative 7 moles per liter. If you plug that into the equation for pH, you find that water has a pH of 7. pH equals negative log of 1.0 times 10 to the negative 7. That equals negative 1 times negative 7, which equals 7. It's a lot easier to write pH 7 than the concentration of H plus ions is 1.0 times 10 to the negative 7, but they mean the same thing. All substances that have a pH of 7 are neutral. This means there is an equal concentration of H plus ions and OH minus ions. If the pH is less than 7, it's an acid. That's when there are more H plus ions than OH minus ions. If the pH is greater than 7, it's a base. That means more OH minus ions than H plus ions. Another way to think about this is that the concentration of H plus and OH minus ions depend on each other. The more H plus ions there are in a solution, the fewer OH minus ions. The more OH- ions there are in a solution, the fewer H+ ions. We can express this mathematically. For aqueous solutions, the product of H+ and OH- ions is a constant. The concentration of H+ ions times the concentration of OH- ions equals 1 times 10 to the negative 14. Take another look at the formula for pH. Notice that because of the negative sign in front of the log, the pH decreases as the concentration of H+ increases. And because the scale is log-based 10, each difference in pH represents a 10-fold difference in the concentration of H+ ions. A substance with pH 6 has 10 times more hydrogen ions than water has with a pH of 7. A substance with pH 5 has 100 times more H+ ions than pH 7. pH 4 has 1,000 times more H+ ions, and so on. Let's see a real-world example. Lemon juice is acidic. It has a pH of 2. What is the concentration of H+ ions in lemon juice? We can figure this out using the equation for pH. pH equals negative log of the concentration of H+ ions. Substitute in 2 for pH. Divide both sides by -1 so the log is on its own. -2 equals log of the concentration of H+ ions. We can get rid of the log on the right by taking the antilog, or inverse log, of both sides. This means we have 10 to the -2 on the left and 10 to the log of the concentration of H+ ions on the right. That gets rid of the log on the right, leaving just the concentration of H+ ions. 0.01 equals the concentration of H+ ions. We can write this using scientific notation. The concentration of H+ ions equals 1 times 10 to the -2 moles per liter. Let's try another example. What's something you use in your daily life that is a base? The detergent you use to wash your clothes feels quite slippery when it dissolves in water. That's a sign that it's basic. The typical pH of washing detergent is 8.5. What is the concentration of H+ ions in this solution? pH equals negative log of the concentration of H+ ions. -8.5 equals the log of the concentration of H+ ions. Take the antilog, or inverse log, of both sides. 10 to the -8.5 equals 10 to the log of the concentration of H+ ions. The concentration of H+ ions equals 3.16 times 10 to the -9 moles per liter. Notice that this is much less H+ than in lemon juice. Here's one last example. Your favorite soda has a concentration of H+ ions of 3.16 times 10 to the -3 moles per liter. What's the soda's pH? pH equals negative log of the concentration of H+ ions. So pH equals negative log of 3.16 times 10 to the -3. pH equals 2.5. Wow, that's pretty acidic. Here are some average pH values of other common substances. Which ones do you find surprising?